Hello and welcome to lab number 4, oscillations and energy conservation. Here's a brief preview of our end results. A table of contents. We're going to go through essential concepts, then explaining the code, and then our analysis at the end. So first off, we're going to start off with two basic kinds of things that we're going to be dealing with in terms of formulas. First, energy conservation. So the energy of the system is going to be equivalent to the surrounding work plus Q. We're not really dealing with Q, but there's no surroundings, so we'll deal with that in a second. However, the three formulas for our potential energies are spring potential energy, which is this, kinetic energy, which is this, and potential gravitational energy, which is this. Since we're close to the Earth, we're not using a complicated one. Then, of course, for the coding purposes, we're going to be using a lot of kinematic position and velocity equations, but we've done that pretty frequently, just calculating Fnet and plugging into these to get their respective movements. The initial conditions of the system, we're going to have a spring force pointing upwards as we are moving the spring past its relaxed length. It's going to be pushing upwards against the force of gravity, which is moving the exact opposite direction in equal and opposite force. As you can see here, they're equal and opposite. And since there's no work from the surroundings, and we aren't dealing with Q in this scenario, it is safe to assume that the change in energy in the system is equivalent to 0 since there's no work from the surroundings. And that means that we can translate this equation into this, which all your initial energies is equal to all your final energies. Here's the tracker video. As you can see all the X and Y values being outputted as such when clicking play, and the X and Y tables as such here. So let's explain the code real quick. So for our initial values, our ball mass was given in the pre-lecture video, and our initial position is the first two X and Y values in the CSV file or the Excel file, which are both here. And we use some more initial values. G is self-explanatory. We calculated our spring constant by using the oscillation formula and kind of calculating how long it takes between the cycles of the spring via these two graphs, and then plugging that into this equation to solve for K using this oscillation formula. Pretty complicated, but we eventually got it out to be 6.83 newtons per meter. And then for our relaxed length, we could use this equation as such to calculate it. Because we have K and we have the length that is currently out, we can just solve it for relaxed length using the force being equivalent to mg, since your force of the spring is going to be equivalent to mg because it's equal and opposite as explained here. So after that, we need the spring length values to plug into some of our equations. So L is just going to be the position minus string position. It's just the length of the string, or the length of the ball, which makes sense. Or length of the spring, I apologize, which makes sense. Then your L hat is just going to be how you calculate any other hat value, magnitude being divided from your vector format. Then your S is going to just be that in this format as such right here, which we can plug into our spring potential energy formula, which is right here. You can plug it in here, so you're going to get our spring potential energy here, our potential gravitational energy here, and our kinetic energy here using these formulas. And then our total energy is equivalent to 0 as we discussed earlier. Forces of movement. Our time is 6.648 seconds, as calculated in the video how long it was moving. This is just an iteration loop where our initial values are what we calculated here. And then our gravitational force is as such, our spring force is as such, and adding them together is going to be equivalent to a Fnet, which makes sense adding them together. And we can plug that into our commonly used velocity update and position update formula to get movement from the ball in the spring. And this is just our iteration where you can see that we're calculating all the kinetic and two different potential forces and then graphing them. And that graph can be seen in this video right here. As you can see, you have your oscillating potential gravitational and potential spring energy, and then a bit of kinetic in there as well, which we'll explain in a second. So this graph proves that the delta E in the system is equivalent to 0 since these formulas, the positives and negatives, are canceling out exactly. So leaving with a delta E of 0 as represented by that orange line. And it represents that equation. As for the X and Y graphs, they're a little bit off from the model and the experimental. Potential sources of error include air resistance, miscalculated initial velocity, which it isn't 0, 0, 0 as I put in the code, or a wrong delta T interval, too large, too small, which I couldn't figure out how to calculate because I'm not very smart. Is the inverse principle satisfied? It is. We explained it up here that since the delta U of the system and these are all canceling each other out, it's going to be equivalent to 0, which is correct. Oscillation estimates. This is by going from here to here. You can estimate that the oscillation period based on the X graph is about 1.6 to 1.7 seconds, and the oscillation period for the Y graph is about 1.5 seconds. Since these are different, it basically just means that you need to calculate the spring constant using oscillation periods of not a singular axis. So yeah, thank you so much for watching, and enjoy your day. Bye-bye.